Hi, and welcome back to our flipped chemistry classroom, and we're continuing our conversation about gas laws. So we've learned 6 gas laws now. We've learned Boyle's law that relates pressure and volume. We've learned Charles' law that relates volume and temperature. We have learned Gay-Lussac's law that relates pressure and temperature. We have learned Dalton's partial law. We have learned Avogadro's law that relates moles and pressure. And so now we have moles and volume, one last law to learn, and that's the ideal gas law. So our ideal gas law kind of takes all of those variables and puts them together. So we already know that volume is proportional to moles. We can relate the volume, pressure, temperature, and moles. And now we want to take one law that, rather than talking about what happens when things are changed, we want to be able to calculate at a given condition, a given volume, pressure, and temperature, how many moles are present, or given number of moles and pressure and temperature, what's the volume? And so we're going to take what we've learned about gases and ideal gases. So remember that an ideal gas, is one that obeys all of the tenets of the kinetic molecular theory. So an ideal gas exerts no forces on its other molecules, has pressure directly proportional to the number of collisions. The particles have zero volume. The temperature is directly proportional to kinetic energy. So all of those pieces. And we know that real gases aren't ideal, but in most conditions, they behave ideally enough that we're able to make these calculations using the ideal gas law. And so our ideal gas law is PV equals nRT, where P stands for pressure in atmospheres. Now notice that in our other gas laws, we were able to use any pressure unit that we wanted. We just had to be consistent about using the same pressure. Now we specifically need to be using pressure in atmospheres. We also have volume, and that has to be in liters. And again, before we were allowed to use different units as long as we were internally consistent, but now volume has to be in liters. N, just like the Avogadro's law, stands for the number of moles. Now, R is new. R is our proportionality constant. This is also called a gas law constant. And the R is 0.08206 liters times atmospheres divided by moles times Kelvin. And this constant is why we have to have our pressure in atmospheres and our volume in liters so that all of our units cancel out. And of course, T is temperature, which, just like all our other gas laws, has to be in Kelvin. So R is a constant, it doesn't change. The pressure, the volume, the number of moles, and the temperature can all change. And this holds really closely as long as pressure is not too high. We're going to treat it as if it works in all circumstances. Again, knowing that real gases are not ideal, but they're close enough that we can work with it. So let's take a look at a couple of examples. So our first example says, at what temperature would 2.10 moles of nitrogen gas have a pressure of 1.25 atmospheres in a 25-liter tank? So we're going to take just a second to switch cameras. Okay, so we've switched to our document camera so that we can practice one of these problems. So our question asks us for temperature. So we know we're looking for temperature. It gives me a number of moles, 2.10 moles. So N equals 2.10 moles. It tells me the pressure, 1.25 atmospheres. Pressure equals 1.25 atmospheres. And it tells me a volume, that's 25.0 liters. And we know R, it's a constant. So R is 0.08206 liters times atmospheres over mole times Kelvin. And so now we're going to use the equation PV equals nRT. And we're going to just take these values and we're going to plug them into our equation. So our pressure is 1.25 atmospheres. Our volume is 25 liters. And you notice that I'm keeping all of these units all the way through this problem. The N is 2.10 moles. R is 0.08206 liter atmospheres per mole Kelvin. And then temperature is the thing we're trying to find. If I'm running out of space here at the end. Okay, so now I want to solve for T that's hiding over here at the end. So I'm going to multiply these two numbers together and then I'm going to divide them by the product of these two numbers. And so once I do that, and we can see that the atmospheres are going to cancel out, the liters are going to cancel out. I'm multiplying by moles, and I'm going to be dividing by this. So my units in the end here are going to be in Kelvin. And so, we have a final temperature of 181 Kelvin, and that's really cold. That's like negative 90 degrees Celsius. So that's very, very cold. So that's our first example. And this one was pretty straightforward because we were given N, P, V, and we always have R, and we were just solving for T. But let's try one that's a little bit more complicated. So now we have, what is the volume of 22.4 grams of carbon dioxide gas at 25 degrees Celsius and 1.12 atmospheres? So I know this is a PV equals nRT problem. It's asking me to find volume. It gives me the pressure, 1.12 atmospheres. It's right here. It says, what is the volume? It gives me a temperature, but it gives me temperature in Celsius. And remember, we have to always be in Kelvin. So we're going to take that 25 degrees Celsius and we're going to add 273 to get that this is 298 Kelvin. And R we have 0.08206 liter atmospheres per mole Kelvin. So I obviously need N if I'm going to solve for V, but I'm not given moles. I am given mass. And so I know that 22.4 grams of carbon dioxide, well, now I can solve for moles by dividing this by the molar mass of carbon dioxide. So I'm going to take the mass of carbon, 12.01, plus 2 times the mass of oxygen, which is 16.00, and we get that it's 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. And this is old hat by now. You guys have been doing this for a long time. So we get that our number of moles is 0.509 moles of carbon dioxide. So N is 0.509 moles. And so now we're going to solve PV equals nRT. And we're going to start a little farther over to the left this time. So our pressure is 1.12 atmospheres. Our volume is what we're trying to find. N is 0.509 moles. R is 0.08206 liter atmospheres per mole Kelvin. And then the temperature is 298 Kelvin. So I'm going to multiply these three together and I'm going to divide by 1.12 atmospheres. And atmospheres are going to cancel out. Moles are going to cancel out. Kelvin are going to cancel out. And my answer is going to be in liters. And so I get a volume of 11.1 liters. And that would be my final answer. Okay, so anytime we have an ideal gas law, we're going to see all of these values, but we're frequently going to be given mass instead of moles. Let's try one more like that. And so we know this is a PV equals nRT problem. This is an ideal gas law problem. It's asking me for pressure. It's giving me a mass, it's giving me a volume, and it's giving me a temperature. So pressure is the thing I'm trying to find. Volume is 33 liters. N, I'm going to have to find again because I'm given mass. R is 0.08206 liter atmospheres per mole Kelvin. And as always, you don't have to memorize that constant. It'll be given to you. The equation will be given to you. You just have to know which equation to use and how to plug things in. Temperature is 21 degrees Celsius, but we need to convert it to Kelvin, so plus 273. So this is 294 Kelvin. And so N, we're going to take the mass of the oxygen, the 48.5 grams of oxygen. And we know there are 32.00 grams of oxygen in 1 mole of oxygen. And so we're going to convert that, and we get that we have 1.52 moles of oxygen. And so this becomes 1.52 moles of oxygen, and PV equals nRT. And so we're going to solve for P. P times 33.0 liters equals 1.52 moles times R, 0.08206 liter atmospheres per mole Kelvin, times the temperature, which is 294 Kelvin. Kelvin cancel out, moles cancel out, liters cancel out, and we solve for pressure, and our pressure comes out to be 1.11 atmospheres. And that's the solution to our problem. As always, I look forward to seeing you in class and answering your questions.